Thank you, Emily. Hello, my name is Julian Hagedorn. I'm system engineer for Buck Boost and Buck Boost controller and converter products in Texas Instruments. Today, I want to talk about our ultra low IQ Buck Boost portfolio, and in particular about our newest addition to the family, the TPS 63900. The TPS 63900 is a 7975 nanoampere quiescent current buck boost converter with an input current limit and dynamic voltage scaling feature. Today I will give you a short overview of our complete portfolio, followed by the ultra-low IQ focus portfolio. And after that, I will discuss the TPS 63900 in more detail and showcase the key benefits of the device on some typical system examples. The Boost and Buck Boost converters and controllers product line offers, as the name says, Boost converters and controllers, and also Buck Boost converter and controllers. Buck Boosts can be used where the input voltage is either higher or lower than the output voltage, or where the output voltage switches between two values which are higher or lower than the input voltage, because it can boost and buck. We also offer flyback and SEPIC controller and converter solutions. Flybacks can be used for isolated or multi-rail power with transformer, and SEPIC is basically a buck boost made of a boost with a coupled inductor, which can be a cost-effective solution compared to a standard buck boost controller or converter. This slide shows a simple selection table of our hero products. And as you can see, we have for almost all our power classes and topologies a suitable part. The parts in red are our hero products for this specific block that you see. And I just want to briefly mention the blue parts here that are currently in product preview. This is the LM5157 and LM51571, which is an asynchronous boost converter for up to 45 volts output voltage, and the LM5127, which is a 42 volts YTN triple buck and boost controller. It has multiple rails here. Right. Today we will focus mostly on this part here in the middle. For completeness, we also have a wide automotive portfolio, but I will skip that for this presentation, but it will be available in the PDF version that will be shared. For completeness, we also have charge pumps and PWM modulators, but there's nothing new at the moment. So let's go straight ahead to our ultra-low IQ boost and buck boost converter portfolio. Here you see on the x-axis the switch current limit, and on the y-axis the quiescent current, roughly, to showcase where the devices are coming from. In blue, we have our boost converter portfolio, and in red, our buck boost converter portfolio. There are several more devices there, but these are the newest additions, and which also focus on low IQ. If we look at the buck boost portion, we have last year released the TPS638XX series with, I think in total 5 parts, which are in the high current, high output current and high switch current side, so with 5 amperes, but offers 11 microamps or 13 microamps quiescent current, depending on which part you look at. There's one version with I2C interface, and the other version is with a standard resistor feedback divider option to program the output voltage. From that, we developed the TPS63900. We just released it 2 months ago, and it brings down the quiescent current significantly to only 75 nanoampere. On the boost side, we do have the TPS61098, released a couple of years ago. This has 300 nanoampere quiescent current, which is the best in class that we have currently for the boost side. But we are constantly updating our products here. So where are ultra-low IQ DC-DC converters typically used and needed? So let's take a look at this simple load profile as an example, where we have a high current phase here, high current phase here, and a lower current phase here. And so in the high current phase, for example, you transmit data via wireless protocol like narrowband IoT, LoRa, or sub-1 gigahertz protocol, which then consumes several tens of milliamps or even hundreds of milliamps. And in this low current or sleep phase, you may just have a MCU or a sensor active that only consumes a few microamps. Now, if this time here in the low current phase is much, much longer than the high current phase, the duty cycle is very low, and the majority of the energy consumption will be here in this block, even though the current is low. And if that is the case, then ultra-low IQ DC-DC converter makes a difference for the battery operating time, for example. This chart here tries to explain it in a slightly different way. Here I plotted the impact of quiescent current on the system current consumption. So we have here the system average current consumption, and here the impact of the IQ on the system average consumption. And I have here several quiescent current values plotted, how they impacted. So if you now look at this 10 milliampere case, you see that the impact of solely the quiescent current is not significant, even though you have, for example, here the 50 microamps quiescent current, so it's only 0.5%. Whereas if you look here at the 10 microampere range, the 50 microampere for sure is out of the chart. But here the difference between a 200 nanoampere and a 50 nanoampere, or let's say the 200 nanoampere and the 1 microampere device is quite significant. So the 1 microampere device contributes for 10% losses in this case, and the 200 nanoampere only for 2% losses. For sure, this is only a simplification because there's also different losses in the system, like the switching losses and leakages from caps and so on. But this should give you a rough ballpark where a ultra-low IQ converter is can bring value to increase efficiency and increase battery operating time. Having said this, let me introduce you to the TPS 63900, our newest ultra-low IQ buck boost converter. It supports a wide input voltage range of 1.8 volts to 5.5 volts, and the output can be programmed in 100 millivolt steps from 1.8 volts to 5 volts. The device supports greater than 400 milliamperes output current for this V-in, V-out configuration, and it has a typical peak current limit of 1.4 amps. The 75 nanoampere IQ into V-in translate to greater than 90% efficiency at 10 microampere load. And it also has a low shutdown current. So if you disable the device via the enable pin, it only consumes 90 nanoampere typically. The device also has a 2-level dynamic voltage scaling feature and a programmable input current limit. This I will explain in a bit more detail in the coming slides. To configure the device, we have this digital to resistor to digital interface here, where you connect one of 15 resistor values to these config pins, and then you can set the 2 different output voltages that you can select via the cell pin, and the input current limit is also configured with these devices, with these resistors. The interface here is only active during startup, and during operation, this interface is turned off so that there is no leakage through the resistors here, and that we can achieve the low quiescent current. And if you need to change the configuration here, then you would need to toggle the enable pin or lower the V-in below the POR threshold. But there's also an app note available how to make a multi-level DVS with this part possible. The device always operates in PFM mode, so pulse frequency modulation mode, and the switching frequency depends on the input and output voltage and the output current, and the output current, and ranges from below 1 Hertz in extreme light load configuration and up to 1.8, 1.9 megahertz at full load and boost operation. This slide here summarizes the features and benefits of the device again, but I will skip that for now. Let's instead focus on a little bit on some performance graphs. So here we have the efficiency of the device. And as you can see, the efficiency here is plotted from 1 microamp until 1 amp, so a very large output current range, and for a few input currents. And the efficiency is above 90% for input voltages between 2.6 and 4.7 volts, starting from 10 microampere and above. And even here at 1 microampere, we still see an efficiency of around 80%, which is quite nice to see. The next graph that I would like to point out here is the maximum output current graph. So you see here the input voltage plotted over the output current for different output voltages. And yeah, even though we usually say that this is a 400 milliampere output current converter, it can deliver much more depending on which operating point you look at. For example, here, if you have a Vin which only goes down to 2.5 volts, then you can ensure that the device delivers more than 650 milliamps at an output voltage of 3.3 volts. The quiescent current, I just briefly want to highlight here that we have the 75 nanoampere quiescent current typically over the whole Vin range. And the output voltage ripple over several output voltages here below 50 millivolts with one 22 microfarad 0603 capacitor, and this can be definitely reduced further if you add additional output caps. However, adding more output caps will impact the quiescent current due to the leakage of the ceramic caps, which are in the range of 10 nanoamps typically. Okay, let's go through the three system examples that I prepared. And let's start with the two-level dynamic voltage scaling. Here we have an example of a wireless environmental sensor block diagram. We have a lithium manganese oxide battery as an input with a typical voltage of 3 volts. And on the output side, we have a microcontroller, a sensor, and an RF module. The MCU and the sensor are always active to measure the environmental data like temperature, and the RF module is only active maybe, let's say, once a day to transmit the sensor data to a central data collection point with maybe narrowband IoT. These RF modules here usually have, or typically have, a supply voltage of 3.6 volts in order to have a high transmit power. So they can also have lower supply voltages, but that will also reduce the transmit power and therefore the transmission range of the RF signal. The MCU, or the microcontroller, and the sensor can usually be supplied by a 1.8 volt supply, and to achieve that, here we would need an LDO, and then in the system you would actually only need a boost converter, because you boost from the 3 volts up to 3.6 volts, and the whole system here is running from the 3.6 volts. But with that, you always have a huge voltage drop in the LDO, and you lose a lot of efficiency here, especially if you only transmit your data once a day. And this transmission maybe lasts, takes maybe 1 minute, let's say. 23 hours and 95 minutes, you're wasting energy here in the LDO if you go with this operating scheme. So what you can do is to implement the dynamic voltage scaling, or use the dynamic voltage scaling of the spec boost to lower the input voltage of the LDO to, for example, 2.1 volts, to reduce the losses in the LDO. And if the MCU or sensor can also tolerate 3.6 volts, then you would not need the LDO at all, and you can then toggle between 3.6 and 1.8 volts, for example. So how does the DVS feature look like in reality? For high load output, we see this defined output voltage ramp up and ramp downs. And this is in steps of 100 millivolts per 125 microseconds. And this is also true for light loads. For the rising output voltage, but if you have a falling output voltage, that since the device cannot sink currents, so it does not allow any current flowing from the output to the input, the discharge here of the output capacitor is only defined by the output load current. The nice thing is that the device will not switch in this time and will not contribute to any losses. But does that help to reduce operating time, you may ask? Well, yeah, it helps. It did some study on this here in this application note, where we compared the TPS63 900 with the closest competitor device that we found, which has a 300 nanoampere quiescent current, but does not support the DVS, the dynamic voltage scaling function. The load profile here that we used is a narrowband IoT load case, so 250 milliampere current for 400 millisecond time, and we are in 6 hours in a sleep state for 10 with 10 microampere load. And if we compare these two devices without changing the output voltage, we already have a slight battery lifetime increase of 9% due to the lower IQ or the higher efficiency of the TPS63 900. And if we then include also the dynamic voltage scaling feature, so we lower the output voltage, we lose a few efficiency points here compared to the 3.6 volt output voltage. But still the input current is reduced, and therefore also the input charge drained from the battery. And this gives us a battery life, extended battery life of roughly 50% compared to the competition device. And further details can be found here in this application note. Yeah, this slide basically shows this in a slightly different way. And here's a reference point for different system average currents. And the at low system average currents, difference between high, medium quiescent current part and a low quiescent current part is not so significant. But if you have a lower quiescent current, lower system average current, the difference here is very significant. And with DVS, you gain even more battery lifetime. The next feature that I would like to highlight is the programmable input current limit. The input current limit can be programmed via the config pins, the 3 config pins on the device, between 1 and 100 milliamps, or it can be turned off, and then the converter is limited by the peak current limit of 1.4 amps. And if we look here at this application, like a smart meter, usually non-rechargeable lithium ternary chloride batteries are used, and those are especially good for this type of application because they have a high capacity, high energy density, and a low self-discharge rates. So you can, they're an ideal candidate for these long-term applications. However, these batteries also have a limited output current capability depending on the discharge rate. and the capacity can vary significantly, which is shown here. So if you look at this graph here from this Tadiran battery at this curve number 3, which is the typical temperature case, the rated battery capacity is 8.5 ampere hours here at 2 milliampere average load current. And if this average load current goes up to only 10 milliamps, you lose the capacity will be degraded to 6 ampere hours, which is a reduction of 30%, which is quite big. So typically you put an HLC or other big capacitor in parallel with the battery to support high pulse current loads in this. But then you do not have a controlled charging of this capacitor in parallel to the battery. And if you discharge the capacitor always, then you always have this pulse load profile on your battery because you always need to recharge the capacitor as well. With the input current limit of TPS 63900, you can solve this problem to some extent, so that you have the capacitor sitting after the converter, and then you have a controlled. Then you can have a controlled charging of the capacitor all the time. And in most of the cases, you can also size this capacitor smaller than compared to have it directly parallel to the battery. With an additional load switch, you can combine the input current limit and the previously described dynamic voltage scaling feature as shown here to even increase the system, the battery lifetime even more. How does this the input current limit performance look like? So the efficiency is not impacted if you enable this input current limit. So you see here all these 3 lines are on top of each other from 1 microampere to 100 milliamps. Then during operation, I have here set the input current limit to 2.5 milliamps and applied a 100 milliampere load transient to the output. And you can see that the device is limiting the input current nicely to average 2.5 milliamps and it's charging the output cap again over this 30 milliseconds. The input current limit is also available or active during startup as well. So if you have a big output cap connected to the device, the output voltage will rise monotonously and will simply charge the output cap. The last feature that I quickly want to describe is to parallelize the device. So if you, so the device can deliver more than 400 milliampere output current, but sometimes that is not enough. So if you look here at this example of a wireless network camera, you have certain blocks that have a high output current and maybe one block which is always active when the camera is just waiting for someone walking past the camera to take a picture or to take a video. And this block consumes only a few microamperes in sleep mode. And then you could use the TPS 63900 to power this to have a good efficiency at this light load and use a high current buck boost converter for all the other blocks here. But this would have the drawback that you have 2 devices on your BOM list. and you could reduce this BOM list by one device and adding a second but TPS 63900 in parallel, which then need to be programmed to the same output voltage level, and then they can share the load and provide the current for this output load here together. And then you have a system which consumes only a few nanoamps quiescent current when it's in sleep mode, but also can deliver the high current when it's needed. What does that mean for efficiency? So for sure, at low loads, the efficiency is impacted because you have multiple devices in parallel. So the quiescent current adds up. For higher currents, the efficiency is not impacted and is even get a little bit boosted here in the high current range. The output current gets multiplied by the number of devices that you can attach, and you can even add more if needed. So there's no basically limit to the device. And the only thing that you need to do is to program the device output to the same output voltage level. Here I still have one picture that shows the stability of the system with, here, example, 2 devices. I have a load transient from 0 to 1.7 ampere. With, I think, a 10 microsecond rise time of the load step. And the output voltage only drops here by roughly 150 millivolts and recovers within a few microseconds and is then stabilized. Last but not least, I would like to show you this slide as well with our collateral towards this device, which is already for different application. We have different kind of collaterals. We have this startup videos. We have the technical articles and reference designs available, and also an EVM available. And with that, thank you for joining today and for your interest in the TPS 63900 ultra low IQ buck boost converter.
Thank you so much, and thank you everybody for joining today. Just a reminder that these slides will be available and the recording will be available by the end of day today on www.ti.com/NPU. And we have one more webinar next week before the end of the year, and the topic is thermistors. And that will be the last one before we close the year, and we'll kick back up the first week in January. I see we have a few questions in the chat, so we will stay on. A few of our experts will stay on and help answer some of these questions just for a few more minutes. Thank you, everybody.